afternoon and welcome to the UP Steam Update for April of 2022. How's everybody doing today? Well, I'd like to again welcome everyone here, and on behalf of the Union Pacific and Union Pacific Steam crew, welcome. We have been busily working on the big boy and doing various things around the shop, as we always do, keeping the equipment in good order. And we enjoyed a really nice trip last year. We went down in a very warm part of the country in the hottest time of the year that you can travel down there. And so that was exciting and fun for all of us. Before I begin, I would just like to introduce some of my crew that's here with me. And we have Ted Schulte. Ted is a locomotive engineer and fireman. And you can stand up, it's okay.
He's a low-key operator.
And we have our newest member of our team, John Stravino. John is a Boilermaker welder. And we have the second half of that Boilermaker contingent, Jimmy Thompson. And we also have two members of our water treatment team. We have Bill Bondi with Iron Horse Water Treatment. For those that don't know Bill, he comes from a U.S. Navy background, and he helps us with water softening and various technical aspects of what we do on water treatment. And we have Paul Gershio. So we owe Paul a special debt of gratitude, because Paul, from 1990 onward, was the protector. As to this day, I have him listed in my phone as 4014 Protector Paul Gershio. And so Paul has played a very unique role in the organization with the Rail Giants Museum, the Railway and Locomotive Historical Society. And Paul has spent countless hours prior to the concept of restoring the big boy. He had his hands all over that locomotive. And Paul has been with us every step of the way, haven't you, Paul? Every step of the way. Yep. So thank you, Paul. And I'd also like to introduce my girlfriend, Sandy. All right, well,
Dad,
yes.
before you begin, you have a couple words, John.
Sure. I'll turn the microphone over to my friend.
Hi, for those who don't know me, I'm Butch Wall. I'm president of the Rocky Mountain Division, TCA. And we're John Darberg is our director of shows, and it's his effort why we have these shows. And I know we haven't had one for a couple years. And what we'd like to do is thank Ed. For many years he's come down and given us updates on the big boy, and we really appreciate that. And for that, we'd like to make Ed Dickens an honorary member of the Rocky Mountain Division of TCA. He well deserves that.
John, want to say anything?
All I have to do is say, thanks, Ed. Will you guys get to it?
Thank you. Thank you guys for everything you put on out here.
Thank you. Perfect. It's very generous, very kind. Thank you. So a few words about rail fans and train shows and things like that. Who would ever think in the year 2022 that we would be here talking about a big steam locomotive? That we would be talking about a railroad corporation that operates steam locomotives for the purposes of this: public engagement, enjoyment, rail fanism, the promotion of all types of messages that we have. You see over my right shoulder, safety campaigns, photography awareness, not just steam locomotives, but rail safety awareness in general. Well, not only are we going to talk about a steam locomotive, we're going to talk about a big boy. And many of you, as I look around the room, I see familiar faces, and you've seen some of these presentations before, but I would be remiss if I didn't ask this question: how many people really thought they would ever see a big boy run again? Nobody. And here we are, we're talking about it, and we've got right around just under 14,000 miles on that locomotive. And that comes from a commitment that the Union Pacific has in the preservation of not only our Union Pacific history, but our nation's rail history. So this goes back to 1862 as President Abraham Lincoln and the signing of the Pacific Railway Act, a point when our nation was divided, and he knew that the best and only way was to unite the nation with the railroad. And that Union Pacific logo is unchanged to this day, despite all the mergers and things, the corporate structures and changes, that has not changed. So we're very proud of that. When we were putting the locomotive together, we had originally had 5 years, a little over 5 years. And as things worked out, we had to do some work on the other locomotives. Most people know the story. We did some work on the 844. I'm just going to talk about that a little bit. But we were able to put this big boy locomotive together in 2.5 years. So I've got some additional photographs. I don't want to spend a lot of time on that. It's really interesting, and I could spend hours telling you all the work that we did and showing all this tremendous, very hard work and very complex part of rebuilding the big boy. So we'll just dive right in. If it's okay, I'm going to sit down as I've got to run my computer here. And here we are, very iconic location. This part of the trip is something that we really don't announce. And it's something that came together within the last several weeks of planning the big boy. Was able to position the locomotive on the terminal railway of St. Louis, right here in this view that you see. In order to get the locomotive there, we had to negotiate a few tight curves, but the big boy, being a big articulated, has no problem doing that. And here's one of my favorite photographs. I always like to include this one. Look at the size difference between the two. The angle where I'm standing gives the appearance that the big boy is bigger. Dimensionally, it's almost the same height as the 844, but that represents two 844s. And when you're in the cab looking down, you're looking down into the cab of the 844, which in itself is a massive locomotive. I don't know who was putting their thumbs up. What do they call that when somebody photobombs? Yeah, somebody was photobombing with their thumb. But when we operate the locomotive, we see so much and we experience such a fabulous way to see America and see the Union Pacific Railroad. But there's so much focus and concentration and planning that goes into these trips and executing the trips that we don't often have the time that I wish we did. And going forward, I always say that I want to do more and I want to figure out how we can capture these moments. So I take a few minutes whenever I can to do just that. And just a quick shot of the cab of the 844, just a beautiful locomotive. And this was following our rebuild of the boiler, as I mentioned, that I'll get into here in just a little while. And now we're looking down into the cab of the big boy when we were putting that locomotive together. Piecing it together in such a way as to make as many useful changes as we needed to do the servicing. And that's what I want to talk a little bit about is the servicing and the operation and the water treatment of steam locomotives. Just because the locomotive is put back together again and it's operational, when we operate it, we're boiling water naturally, and that water has an effect on the steel. And there's lots of chemical additives and chemical products that result from boiling that water that just continue to work very aggressively on certain parts of the locomotive. So we do a lot of cleaning and a lot of servicing, which is why they got rid of the steam locomotive, because of the very burdensome mechanical aspect of maintaining the locomotive. Here, for those of you that haven't seen this, I actually have this number plate, and I wanted to bring it as a way of illustrating just the size of everything, just the sheer size of all these components and how big and roomy the cab is. You can see as we're putting the locomotive together, we're fitting everything up. But where the engineer and firemen sit, actually on this raised portion of the floor, and here's this number plate right here, just to give you a sense how big that is. So every year, annually, we're required by federal regulation to disassemble the locomotive to a degree. We separate the engine and tender, and then we begin a scope of work into the boiler. So what we need to do is we clean everything and we inspect it. And one of the things that we do is we subject it to hydraulic pressure. So we go 125% over what we call the maximum allowable working pressure. And that takes our pressure gauge, which is normally sitting at 300, we shove it all the way over to 375 PSI, warm water hydraulic pressure. And as we do that, we're able to determine that the boiler is exactly what we need it to be. A hardcore, heavy-duty industrial steam generating power plant. And that locomotive, when we're traveling down the track, it doesn't always develop 7,000 horsepower, but it's capable of developing that much power. So we get down on the inside of things and we're looking at all the internal components and we're inspecting everything. As we're going down the track, these springs, when you're sitting there looking at them right now, they're heavy duty and they were really something when we put them in there. To get those springs in place took a lot of physical brute force. And in some cases, you can't really get a lot of machinery there. So your body, or several of us, our bodies are down in there manipulating these big components. When this locomotive is going down the track, these springs are transmitting the weight of the locomotive on top of the drivers. And that's what produces the tractive force, or what allows a locomotive to produce the tractive force is the adhesion. So when these springs, when you're going down the track, these things are actually moving quite a lot. And these are brand new, as are these components and some more of the suspension components that we inspect every day. So as we come into any place where we stop, do you remember anybody ever look at the old photographs of old locomotives and the engineer is off with a big oil can in his hand? And the fireman, he's usually attending to his duties, firing the locomotive, but any opportunity they had, they were on the ground oiling things and physically looking at things, and in some cases tapping things with a small hammer to verify everything was in the proper condition. On these big locomotives, we don't have to oil everything manually. All of that is done through an automatic process that they developed for these locomotives. But we still have to look at everything. When we put the locomotive together, as I mentioned, we made all the new parts that we possibly could, all the new parts that we absolutely had to, in order to give us what we have. So you can see these big heavy bolts. And Ted, I think we have one over there. One of those spring rigging pins. And big giant springs on all the big giant heavy components of the boiler. So that's what we're looking for when we do that annual work. You know, how we care for the locomotive, how we operate it, all of that works in concert with all of the detail that you see here. This is right after we got through putting the locomotive together. We do not disassemble it to this extent during the annual inspection, but let's say that we discovered one of these stay bolts was broken up here. If we had to, we'd have to either cut away part of the cab or physically pull the cab off in order to do that repair. So that's how serious the annual inspection is. That's what Jimmy does, that's what John is learning. You know, the fine art of that type of welding and removal of these big heavy-duty components. The front engine, when it's removed from the locomotive, if there were a big problem on the locomotive that we had to address, the only way to get to some of these components is to remove the front engine. Well, that is a very big job, and that's something that you're not going to do in an afternoon. So all of the procedures that we've adopted and everything that we do is the same procedures that the Union Pacific would have done back when they were operating these locomotives. And when I tell you this, I'm serious in that there was a sigh of relief when the steam locomotives were replaced because of all this tremendously difficult, very burdensome scope of work. Here's some more of the just outstanding machine work that Garland Baker assembled. This is an eccentric link and what we call the link trunnion. So that the link, as the locomotive is operating down the track, I'll show you the next view here. This link is what controls the radius watt, which controls the valve. And when you're operating at speed, these components are moving very rapidly. They're changing direction dozens of times a minute. And so they have to be able to withstand the tremendous inertia forces and just the physical force of that locomotive when it's operating. Here's the bearing inside. A nice new modern spherical roller bearing, which coincidentally is still available today. Over time, modern industry with the American railroad system, not only Union Pacific, but all the railroads, many of the manufacturing companies were finding ways to either repurpose or use similar dimensions off railroad equipment. That's how some of this equipment is still available today. Some of the other work that we've done, we've kind of put a few finishing touches on there. Oftentimes we look at Facebook and some of the comments on social media, and people want to know what the chain is used for, and if we're going to put what we call a chain guard on, so we've done that. So inside here, we went a few steps beyond what the UP would have done. The chain guard they had was just a way to keep it from catching on tree branches and other things. So we have some Teflon liners in here that are actually carrying the weight of that chain. So over the course of operating it, that chain is moving back. It's flailing around. About over 35 miles an hour, that chain really starts to bouncing. 45 miles an hour, it's going left and right and up and down. It's really, really rocking and rolling there. But what the chain does is it's actuated by this sprocket, and it's simply moving back and forth, operating the lubrication system that I mentioned to you a little bit ago. So up here we've got the big giant articulation centering device spring, and the centering device rod. And we added some additional oil reservoir capacity for our lubricators. So we've got a transfer line that allows us to add extra oil. So we don't have to stop and say 25 or 30 miles and fill that reservoir back up. We have all of the reservoir capacity we need to go, usually about 80 miles. Sometimes we don't really want to go beyond that. Working on the big giant rods. When we put the locomotive together, we were not able to completely disassemble it to the extent we wanted to. So we did that back in 2020, and we finished it up just a little bit before we started running in 2021. So these are photographs just before we left on our last trip. But these components, if you've stood next to the big boy, you know how big they are. But look at how beautiful they are. This is Ted's handiwork. Ted gets the detailed jobs. The jobs that a lot of people may not have the patience for, Ted does. Ted has the detail and the patience that he will spend days cleaning, polishing this metal to near perfection. Look at that. To determine that there's no material defects in these rods. Because as we're operating down the track, these components are under tremendous strain and pressure. Not only the thrust of the piston and the 7,000 horsepower developed at the cylinders, but it's withstanding the rotational, or what we call inertia forces. Just these heavy components spinning around. So it's a very important part of the job, and that's what Ted does. These are the old pieces that we pulled out of there. That in itself took several days. They're pressed in, and we don't want to press them back out because this is all we have. We don't have replacement parts. I may not see it in my career, but if I do, what we'll do is we'll make these new components. And that's not as easy as it sounds because these are forgings. It's a special metallurgy and a special manufacturing process. So when we pull these out, we weld that in there, and that draws the metal in there and allows us to pull those bushings out. And we reassemble everything with liquid nitrogen. We shrink everything down, we have a big tank, we submerge the components, and we freeze them about 200 degrees below zero. and then the components slip together very accurately. And here we are putting the main rod with a new bushing into what we call our crosshead. Now this crosshead is the original one. You can see it's beat up a little bit. It's lived a tough life. It's operated over 1 million miles back from 1941 until 1959. The component that it fits in, that's called the crosshead guide, that is brand new. It's 2 pieces, and it's all brand new. We made that, machined all these surfaces here, put everything together beautifully. Some of the more suspension components for the front engine, this is just a big massive piece, big suspension pins and everything on the inside. And this is what Jimmy will look at when he's underneath the locomotive every day. There are times when we don't do an underside inspection. Maybe we didn't really travel that far that day, but generally speaking, you always do a locomotive inspection walking around it. That takes about 45 minutes. If you're going to do the underside inspection in addition to that, it's about an hour and a half. Wouldn't you say, Jimmy?
Yeah.
Yep. Jimmy is outstanding. And so when you're underneath the locomotive, you're really under tight quarters, and we have somebody, it's typically Ted, assigned to him to help with that. A view of the front engine, the front engine truck, all brand new components. Jimmy's checking all of this stuff out on the underside of that. All of the new springs and all of the suspension equipment and everything down underneath, making sure everything's being lubricated. And I will tell you, after 14,000 miles really is not that much. When you think about it in that terms, you think that's a lot, but in the context of what the locomotives operated typically, they were probably right around 10 to 12,000 miles in a month back when they were in regular service. But everything on the locomotive, it looks dirty, but when we clean it up, it looks just like it did when we put it together. Now here's a really important part of the locomotive, and that's the firebox. This is the area where the fuel is burned. And this is just as we were putting it together, converting it from burning coal to burning oil. You can see the circulators just right on the top of the photograph here. But we're putting a big heavy-duty steel framework which will carry part of, or the front part of what we call the fire pan. And this little opening right here, there's my head sticking through it, this is where the burner goes. And so this is all 3/8 plate fabricated to hold the refractory lining that goes in there when we burn the fuel. So the oil conversion is really a popular topic of discussion, and even till this day it generates a lot of interest on our social media, and people are just curious about how it works. And I'll explain it. It's actually quite simple. So the burner, and we actually have a brand new casting over there that you're welcome to look at during our question session. The burner itself is very simple. So remember, on all machinery, anything complex, complicated, or with a lot of little delicate parts isn't going to hold up too good on a railroad. On a steam locomotive, it's going to eat it up and spit it right out. So it has to be extremely simple. So what you have is you have oil flowing, controlled by a valve in the cab, and it's flowing by gravity from a tank. And that oil flows down, and it flows over a small jet of steam called an atomizer. And that steam atomizes that flame into what we call the flame channel, and it hits this area here known as a target wall. And that flame curls up, and it envelops this entire area of the firebox. So when the big boys were designed, they were designed to burn Wyoming coal. And that coal has a very specific heat content, and therefore when you calculate that type of fuel, you need a specific amount of surface area in order to produce the power needed. Well, on an oil burning locomotive, we do not need this area here. We call this the burner deck. So the only area we need for burning our fuel is here. And when we're underway, that fuel oil, the fireball that is developed from the fuel burning, envelops this entire area. If you were able to develop some type of camera that could withstand 2,000 degrees and could actually get some good video coverage, you would see nothing but almost the whiteness of the sun just a tremendously hot fire burning in here. And that heat simply transfers through the heat transfer surfaces. Let me back up here. My computer doesn't want to cooperate. So these are the heat transfer surfaces. And these are the circulators. This is Jimmy's handwriting there. He's gone through and he tests all of that. Oh, I see, okay. So here I am happily pointing away, and you guys are wondering what it is I'm talking about. I apologize for that. You can kind of see my pointer a little bit. There we go. I apologize for that, thank you. So I got to back up 10 slides? I won't put you through that. So these are the heat transfer surfaces here. And these are the circulators with Jimmy's writing. And this is the burner deck that I mentioned, the area that's not needed. So that's really the essence of the oil conversion on the big boy. You know, it's something that I think people have a hard time getting their head around. Well, how does this thing work? And it's very, very simple. And this is a very similar design. Most oil burners have arrangements similar to this. This is simply an upscaled version of what we developed in the 844. And I say we, it's not us, it's what the Union Pacific developed. We've tweaked it, we've made a few little modifications here and there. This is a little brickwork that I developed. I'm a person that likes that kind of work, and you really can only fit one person in there. So Paul is helping, Ted, everybody's Jimmy, they're giving me breaks, and I'm just kind of laying these things in there.
Is that on the floor or is that on a wall?
Also does, I'm sorry? On the oil conversion? Yeah, we just kind of work through the calculations and draw it in CAD. That's what Austin's really, really strong at, really good computer stuff. I'm of the generation where I missed out on a lot of the computer stuff, and I happily admit that I'm okay with that. I've got him. So here's the cab, and it's all 1941. A lot of these fittings, it's interesting to note that we've taken some of these out of our buildings because they're old Pile National fittings. And so Ted and the guys will go over there and they'll demolish some of the old wiring that's no longer used in the roundhouse, for example. And we clean it up and put it in the big boy. More views of the cab. Now, if you could think about if we had to do some of the maintenance that I had mentioned, if we had to pull that cab off in order to do that work, that's what we'd have to do. So that's why our annual work and everything takes place late in the year, and we have throughout Christmas and January, February, March, because if we find a problem, we have to deal with it. And these problems are inherent with steam locomotive designs. As a matter of fact, it's really not considered to be a problem, it's just routine maintenance. And there's a view of the cab and all of the area underneath the cab. I'm getting my pointer here to show up for you. So more views of all of the stables and just the complexity of the machine and how everything fits together. So here we are. This is some of the surface that's exposed to the water. When the locomotive is operating, the steam itself doesn't present a lot of corrosion issues. It does within the boiler, but the actual machinery components themselves, they wear out from the engine sitting. So as we service the locomotive, we want to make sure and get adequate oil in these bushings here. And we made these bushings in the same manner and we made the other components with liquid nitrogen, freezing them together. And this is a fixture that we made to mount the boring fixture so we could bore that dimension. And another real interesting view, and this is some of the work that we did last year, was just confirming that the axles are in the right relationship with each other. So we have some Teflon, very accurately machined with a very accurate center mark that we can measure and determine that these axles are in the correct relationship in the frame. So this is a view you don't get every day. For everybody with a model train, you see this view all the time. Well, this is a 610-ton locomotive, and we're down underneath inside our drop table, and here's the brake rigging and everything. So I want to just stop for a minute and talk about why we have a diesel in the consist with us. And if you look up right here, and Ted, if I could ask you a favor, would you go grab that brake shoe and hold it up for us?
I don't think you can hold it.
So I'm trying to, I think what I'll do is I'm just going to stand up here. Yeah. So this is the brake beam here, and these are called safety hangers. But the brake shoe that Ted's holding there represents about a $250 expense. And they're specially made, so we had the pattern made, and the pattern itself is a wood pattern that's made. It's mounted on a special mounting that the foundry makes. So that pattern, in order to make that takes from start to finish, it's probably, if we were the most important customer at the foundry and they dropped everything and gave us that production, it'd still probably be maybe 3 weeks. So it's not something that you're just going to order. So when we have those made, we make a lot of them, so we have some in the inventory. But there's 4 of these brake shoes. I'm going to try not to step on whatever it was I stepped on. So here's the brake shoe here, and these are the safety hangers that exist, as the name implies, only as a means of catching something. If this big brake beam and everything else were to somehow disassemble itself, it couldn't fall down and derail the train. It is so big and heavy that it'll derail the train. So in order to change the brake shoe on some of these, not all, but some of these brake beams, you have to disassemble this pin and move this so you can fit the brake shoe. Notice there's 2 of them in there. So there's $1,000 worth of brake shoes just on one axle. So that is a little bit of a long explanation on why we have the diesel locomotive. Is the diesel affords us the opportunity to use what we call dynamic braking. Does everybody have an idea what dynamic braking is? For those that don't, it's a motor type of braking that diesel electric locomotives use to slow the movement of a train. On big trains, they need the air brakes as well, but dynamic braking was just a revolutionary advancement and a real improvement over how steam locomotives used to operate. So back to what we're doing in the pit here. On some of these drivers, we had to make slight adjustments in some of the machined components that hold the axles in the frame. And this is what it looks like when the driver is removed. The driver fits right up in here. And while we've got the driver out, we look at all this stuff we need to look at. See all those new pins, new springs, new bolts. And oh, by the way, we had to rebuild the drop table. So it's one thing when you're working on your locomotive, when you have old equipment in the shop, how many times, Ted and Jimmy, John, how many times when we're working on something and we have to fix the part? We kind of have a saying, if it ain't broke, we don't own it. But that's not so much anymore. We've really fixed a lot of components. And another view of the cylinder itself and just all these big heavy components. So if any of these components were to break or experience some kind of mechanical condition where they're really wearing out or there's a big problem with them, you can see what goes into disassembling the locomotive just to get to some of these components, which is building on the story that I'm telling you about maintenance, the care and feeding of a big steam locomotive. Here's one of the valves that fits inside the valve bushings that we were looking at just a few moments ago. And notice you can't see the overhead crane, but we are lifting this with an overhead crane. And 2 guys, probably 3, would really be able to handle this. But how are 3 people going to be able to stuff this thing in there? So having the overhead crane is absolutely invaluable. Well, here we are, we're going to start talking about the boiler. And the heart of the locomotive that boils all that water and produces all the power. This is the clean surface, what we call the shell or the barrel of the boiler. And we have the grid lines that we put on there, just a means of mapping out the ultrasonic test areas that we provided so we can do all the engineering calculations to confirm to the FRA, the Federal Railroad Administration, and for ourselves that this locomotive is absolutely ready to go. Here's a big air filter. It's one of Ted's jobs. Ted is our airman. Brand new main reservoir made by Westinghouse Air Brake Company. And here's one of the night shots that we took and we were putting the locomotive together. We were there late at night. A couple of us lived in the shop for 4 months. We never even went home. Thank you. And here's another view looking down on the very front part of the locomotive, and the engine is so big it has 2 sand domes. Each sand dome has several tons of sand, and that's what these big brackets and these big angle irons hold that sand dome. And when they designed the locomotive, they were very, very efficient on what they did and how they did it. So to access the top check, you actually have to open a hatch on the sand dome. Really good design. And a view of showing Jimmy's handiwork. You can almost see all the new stable caps that Jimmy welded. Jimmy, how many did you do in a day?
Probably about 200.
200. Think about that. How many did you do in one day?
About 200 a day, and I think we replaced about 2,000.
Think about that. All the welding that goes into that. Yep. Now this is the inside of the barrel of the boiler, and this is where it will be interesting. So when you take a steam locomotive and you put it back in service, it's been in service for many, many years, and over the lifespan of the locomotive, scale will accumulate on certain parts of the locomotive boiler. On the front part where the water enters the boiler, at that moment is when the scaling minerals of calcium and magnesium precipitate out of the water and attach themselves to these metal components. So we cleaned all of that off, and this is what it looked like when we painted it and we were ready to go back together again. These big giant braces here. And here's another view, what we call the front tube sheet braces. These are very heavy duty, and they're bracing, as the name implies, holding that surface of the boiler that is flat, that is not self-supporting like a cylindrical plate or a dome end or the barrel of the boiler where it's of cylindrical shape and it supports itself. So that mechanical support is provided by these heavy-duty giant braces and brace feet, and these giant brace feet that are riveted. Well, here you can see the front tube sheet, and I want you to remember that, because I've got a picture to show you in a minute. And these holes are where all your tubes and flues go. And here's a nice shot of a big giant chunk of the boiler that we made new. So back in the days when the Union Pacific gave the locomotive to California, to Paul and his colleagues out there at the Rail Giants Museum, for years and years prior to that, the locomotive sat in Cheyenne, and water got down the smokestack, and it went down through the tubes and flues, and it got down into this part of the combustion chamber, and it deteriorated that material. So what happens is we have what's known as a corrosion allowance. So from an engineering standpoint, the plate thickness is designed to be a specific dimension. Over the life of that boiler, corrosion will reduce the thickness of the metal, and therefore eventually over time reduce how much that plate can withstand. When it gets below what we call the minimum standard, it can no longer serve as a boiler anymore, and we cut it out and we make it new. Well, rather than tinkering around with a little piece here and a little piece there, we just cut an entire section out and make it all new. This is known as the rear tube sheet, and we made that all new. That's just what you must do. This is the other part of it here, coming up the other side, and this is a shot showing the installation of the tubes and flues. Now you have a pressure vessel that can contain water that you can boil and raise to 425 degrees, which is 300 psi. And this is what it looks like when you're inside, putting the last of the tubes in there. Look at how much area you have for water circulation. So if you have an accumulation of scale, it will reduce the water circulation, which reduces the heat transfer, and you can see where I'm going with this. It continues to reduce the overall efficiency of the locomotive. Not only is it reducing the circulation, but it impedes the transfer of heat into these very hot tubes, which have the combustion gases flowing through them at a very high rate of flow. And here's a shot. This is the very first tubes that we put in the big boy. Look at the thickness of that front tube sheet. Yes, that's a very good question, Bruce. His question was, what's the difference between tubes and flues? Tubes are the smaller ones, flues are the larger ones. The flues here, and because my pointer doesn't work, I'll show you. So the tubes here are 2.5, 2.25 inches, and these are the big giant 4-inch superheater flues. And the superheater flues, as the name implies, has a device, a component called a superheater, that takes and flows the steam through and makes a second pass, exposing it to the combustion gases and increasing its temperature and thereby its efficiency and power output. So what happens when you have a locomotive and the water treatment is not being managed? You've got other factors, namely water treatment, and all of the junk and gunk and everything that's in the boiler, and it doesn't get cleaned out. That's what you get. And so you can see this is one of those little small tubes. This is on the 844, and this is the front tube sheet. When we took the 844 apart in 2013, there was a real depressing day. We had some problems, and the problems were a result of just years of that accumulation of material. And so water treatment is a science, it's an art. In refineries, the US Navy, power plants, they manage their water chemistry to that fine science. And the reason they do that is for this very reason here. Because what you're seeing is all of the stuff that's in water. As you boil the water, the pure water steams out as the steam that's being used for propulsion. All of the stuff that remains in the water continues to concentrate, and that's a measurement that we refer to as total dissolved solids, TDS. And then aside from that, you also have the scaling minerals, as I mentioned before, the scaling minerals that will precipitate, that means attached to, like when you go to Glenwood Springs or a hot springs. You see that mineral accumulation. That's exactly what that is. Well, this is on a steam locomotive boiler, you have that. And that's what this is. And so you've got this tremendous, heavy, thick deposit of scale. So I began serving in my role as manager in 2010 and officially took the reins in 2011. And one of the problems that we were having was the scaling accumulation, because I had been in the boilers and I had been present during these inspections. Although I wasn't until I became manager, I didn't have any authority to do anything. So I knew that we had some challenges ahead of us, so I enlisted the support of a few chemical companies to come in and begin giving some analysis on what we needed to do. And so what they did is they sold us these chemical descaling systems. It's a chemical additive, but that just wasn't sufficient. The accumulation of scale was so great that it began to, through the reduction in heat transfer, it was causing the metallurgical changes in the material to where the tubes actually started to detach themselves from that tube plate, the tube sheet. And that is a condition that's just, you cannot tolerate. It's pretty common on steam locomotives to have leaky tubes and flues, but it's something that you have to take seriously. And at 300 PSI, it's an indication that you've got something you need to address. And the way that you manage it is they're only short-term remedies, and the only solution is to disassemble and replace. And that's what we did on the 844. And that's what really took almost 3 years of our timeline that I mentioned at the beginning of the presentation, where we had 5 years to work on the big boy. Well, we spent nearly 3 of that rebuilding this 844, and that 844 is a magnificent locomotive. So now we're going to talk about where the steam goes and what makes the power, and that's these big, beautiful pistons. We redesigned the piston design, the ring, to the same design that the 844 has. This, what we call first series big boys and several series of the 4664 Challengers had a little bit more complicated compression ring design, and over time they improved that design. The 844 has that improved design, and the second series, the 4020 to the 4024, have this design. So that's what we did here. And this is what they look like. Yeah, those are your piston lands. Beautiful work. We welded those up and machined them back down again. Precision ground the piston rods. This is the piston rod for the rear engine. The front engines are quite a bit longer. And look at the box up to the right that says SKF. I can't pronounce that, but it's a company in Sweden that makes very precise bearings. They were able to, it took me about a year's worth of negotiating, but they were able to make me the exact roller bearings for the big boy. And they weren't as expensive as you might think. I mean, parts for this type of specialized machinery, you just have to accept the fact that it's going to be expensive. How many people own a BMW or a Volkswagen, an Audi, a Tesla? You know, those finer machines, or any automobile for that matter today, is expensive to maintain. Take this specialized equipment here. And here we are, again, it's a couple of my favorite colors there. Ted likes to paint things yellow for me. And this is actually some of Ted's handiwork. Those tan lines are copper lines. It's a special grade of thick-walled copper. Excuse me. And all that represents all the lubrication that we have, all the lube lines. And another shot of the driving boxes, we were putting everything together, and the big drivers, and wheeling these big things around the shop. Now this one here weighs almost 19, just say 20,000 pounds. There's 10 tons of wheel. 10 tons of wheel, and you just pick it right up and swing it right where you need it to go. Now we're looking down on the important part of the boiler. This is right in front of the cab where all of the steam comes out for use for the air pumps, the dynamo, atomizer blower, all the accessories. And all of this piping is all brand new. All of these big heavy valves are new. These main turret valves are the original ones that have been rebuilt, extensively rebuilt. Garland has extensively rebuilt these. One of Jimmy's responsibility is, during our 31-day inspection, he will service these. Jimmy and Garland and John will be getting into this as well, is that you take this stuff apart. We're only going to run the locomotive for 30 days. Our upcoming trip will be 37 days. But it's going to take us almost a month to take everything apart, clean it up, and put it back together again. In some areas, we don't put it back together until we're ready to use it because we don't want condensation or moisture to get in there. So there's just a lot of work. Another shot of that brake shoe that you can see just in front of it. And our insulation. When we insulated the boiler, we added 4 inches of insulating material. When we were in Hays, Kansas in 2019, when we woke up that morning, we had snow on part of the boiler. It was that well insulated. So here's a boiler at 425 degrees, and 4 inches away there's sheet metal, and there's a little surface in there, and it didn't have any snow or ice on it. Another real interesting shot of Donnie down there welding on some things, and I'm up in the air in a man lift taking pictures and doing some stuff. And one more shot here looking down at the drivers. What these are for is these allow the locomotive to go around curves, and these are known as a lateral motion device. And these are brand new. The red spring seat and that spring on the other side are new. And we wanted to paint them so as we're underneath the locomotive, the contrast in colors kind of helps us when we're looking at things. It's very dark underneath there. When Jimmy does an inspection, there's things that you're looking for, and your eye adjusts to the locomotive every single day. So when you're under the locomotive, you see things that look like they're in order. Anything that is outside of that, your eye will catch it. We have an inspection hammer, and it's a process that there's several of us, myself, Ted, Austin, and Jimmy, are the only ones that are qualified to do that inspection, because there's so many things that you have to look for, so many things you have to know, all of the detail. The next photograph shows the lubrication on the roller bearing boxes, and those orange plugs, you get a big heavy duty wrench and pull that plug out, and inside this is what you see. The big heavy roller bearings. And then you can see the reflection of that heavy duty oil. It's really comparable to, it's a heavier duty version of what you'd put in your differential on your Cummins or your Ford. This heavy duty stuff. But that's how that axle is rolling down the track with those big giant rollers, and they are big. And here's another interesting, a real neat picture looking down the smokestack. Whenever we do work on the front end of the locomotive, we have to verify that the nozzle, if you look down in there, you can see those, it looks like a Maltese cross down in there. That's what's called a splitter. The little splitter down in there takes the exhaust, as that name implies, and it splits it and it makes it larger. So as that steam is moving up into the stack, it creates what's known as a seal. And that seal creates a vacuum or a negative pressure in the smoke box, and that negative pressure is filled by air from the combustion air on the firebox. So that's what creates your draft. Well, if that nozzle plate, and what we're looking down in the smokestack, and then below that is what we call the petticoat pipe. The railroaders had all these different names, because it looks like a petticoat pipe, like a big tulip. It's flared out at the bottom. If all those get out of adjustment, and think about the force and the pressure on those nozzles, on that steam, that intermittent pressure, if you've seen the big boy operator or any steam locomotive, it is just pummeling. That steam is powering out of there. Well, that creates a lot of pressure on that. And that's what it looks like inside. And there's two grown adults inside this big, massive fire smoke box. It looks like Jimmy. Is it Donnie? Jimmy and Austin, I think, yeah. Yep. And here we are doing some work on our trailing truck. That's a very important part of the locomotive. That bears the weight of the back part of the locomotive and cab. Just big, heavy-duty work that we did. All the reassembly. So the process of reassembling this comes in really handy, because the crew that built this rebuilt it and did all the fine work on is the crew that operates it and inspects it. So our eyes know exactly what we are looking for, and if anything is out of the ordinary, our eyes are going to catch it. Front tube sheet, superheater header, big giant steam lines, big giant swivel joint here, and now we're steaming the engine up, getting ready to go. Big special manifold. As we steam the locomotive up, we have to have the ability to direct that high pressure steam to different parts of the locomotive. And one final shot of the jacket, putting it together with big stainless steel hardware. We put the jacket on the locomotive. I kind of lose track of time. I used to keep a really comprehensive journal, and I just became so busy that I wasn't able to do that. So I kind of forgotten some of this information. I think it was like 7 days, Ted, that we put the jacket on, 5 days. This is just a really quick job. And here's the final shot of the presentation here. Does anybody want to take a guess on what's happened right here? That's right. We derailed the engine. I say we, I mean me. It was one of those situations, and part of what you do when you plan any steam locomotive trip. And the big boy, I have learned to, I guess the best way to say it is step up my game, in that you have to identify the network. And we've got a big, heavy-duty, robust network, and the UP runs millions of tons of trains over this track. But the big boy represents something a little bit more special. And the actual weight of each wheel isn't necessarily any heavier. As a matter of fact, it's a little bit lighter than an SD70 and a big C45 axle loading wise. Those are right at 70,000 pounds an axle, which is 17 tons on one wheel. Well, it's not that much. It's only 16 and a half tons on each one of those wheels. So when the wheels come off the rail, you have to think about that. Whatever you put under the wheel to try to move it back up again is going to get destroyed. So bottom line is you don't want to derail your steam locomotive. In this particular scenario, Ted was there, and my original plan had us going down to the other end of the yard and then backing into the track. I was tired, it was getting late, and I said, let's just go through this crossover. Well, I looked at that crossover about a year before, and I wasn't impressed with it. And I figured, and I don't know why I did it, because the 844 really couldn't go through it. So if we would have made it through, the 844 would have derailed. I don't know what I was thinking. So anyway, we get into the track, and we stopped, and I asked Austin, who's just an outstanding person, I said, walk me through this curve. It's like a thing that we do. Usually we get a lot of people involved in it, but in this instance, I'm just like, let's not make a big deal out of it, but get out there and watch. So he's on the ground watching, and I begin moving forward. I whistle off, whoop, whoop. Ted whistles off, whoop, whoop. And now you've got 1,100 tons of train, 610 tons of big boy, 455 tons of 844, and on and on and on. And so I begin moving, and I hear this, stop, 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 stop. And how are you going to stop? I stopped in 8 feet, but 2 drivers went on the ground. The 6th and 7th drivers. So anyway, we spent 2 hours putting it back up again. But it's a valuable lesson to just remember the planning that I had planned for myself, but I didn't listen to myself.
Didn't the rail kind of roll over?
Nope, the rail didn't roll over. It was just a very slight wide gauge. And it was one of the reasons that I didn't want to use it, was that I identified that. But as I'd mentioned, it was a year and a half prior to that, and I kind of lost track of that little technical detail. You know, I was feeling a little bit comfortable, maybe say cocky, and I paid for that. So with that, we've got a little bit of time. If anyone has any questions they'd like to ask of us, myself, Ted, Jimmy, Paul, John, we're here. Yes.
Is Austin still with the program?
Of course he is. Yes.
Oh, no.
Yeah.
He's not here.
Yeah. Austin's rebuilding the tractor right now. Yeah. Oh yeah. Yes, sir.
What is the sandbox?
Repeat that for me.
What is the sandbox?
The sandbox. Well, there's several of them. There's the sandboxes that we use for traction sand. We call them the sand domes. And they're positioned atop the locomotive so the sand can flow by gravity, and it can stay up there where it's nice and warm and stay dry, so it will flow by gravity. And then on an oil burning locomotive, we've got a sand box in the cab that we use to sand the flues, and that's a process that allows us to get off some of the byproducts of combustion and clean up the tubes and flues a little bit. Good question.
Thank you.
Sir?
How long from cold to operating steam does it take?
His question was, how long does it take us to steam the engine up from it's cold until we're ready to go? Back in the days when they ran these locomotives all the time, they could get them in and out of the shop in a matter of hours. We take a matter of days. It's just a process that we use. We like this big giant boiler. We let the temperature equalize. We've got it full of hot water right now because Monday, Tuesday, Wednesday is our annual FRA hydrostatic inspection that I was speaking of. So it takes us about 3 days to steam it up. We like 4. Good question. Sir?
At a high level, can you talk a little bit about the planning that goes into one of your long distance trips? Do your team actually go out and run the whole route ahead of time, checking clearances, weights, etc.?
Good question. His question was, on a high level, how do we plan a steam trip? That's one of more fun. I will say the funnest part of my job is that. When I started in this role, I knew that I had to drive a lot, and I'm a person that used to hate to drive. I actually rather like it now, fortunately, but I'll drive the entire route. I don't high rail it unless I need to. Over the years that I've been in this role, I've developed a really good understanding of the network and know a lot of it. And I've taken very comprehensive notes. I probably have 100 pages, maybe 120 pages of handwritten, detailed notes of everywhere that we've been, including some detailed OCD level maps. Obsessive compulsive disorder. But my mind has become that way because of all the details that, with the 844 it was important, but with the big boy I have taken it to that extra level. So I'll do that first part of it, and then I work with our clearance and our bridge group, and I'll give them the specific routing that we'll take, and they run the bridge analysis based on the axle loading, what we call the vehicle loading of the steam locomotive, the water cars, the diesel, and the entire consist. And from there, we get speed restrictions based on structure. Clearances are important because of the dimension of the locomotive, namely the swing out and the swing in. So we do all that before we get to a point to where we tell anybody we're going somewhere. So by the time we announce it, which stay tuned for that, we will have done just an enormous amount of work behind the scenes. So I own all of that part of it, and then my colleagues and I, we begin building the plan of the engagement part of the cities and displays and excursions and anything else that we put into that. But the operational piece is all me. And it really needs to reside with my role, because you know what the locomotive is going to be doing, and you will be running it. You know, those of us that run the locomotive, we will be running it, and we're going to have very detailed notes resulting from the plan that we're aware of about Tunnel 3 in the Cascades. We've got 6 inches of clearance, or 3 inches of clearance between the tunnel wall, because it's a 9-degree curve. Well, I've got that written down already. So it's a very important part of the detail.
Just out of curiosity, will you be running 844 this year, or?
His question was running 844 this year. We had initially planned to do that, and we just decided that we won't. We all were really looking forward to it. We were all ready to go, getting things ready to go, but we've got some other things that we're working on. So as much as we like that locomotive, as much as everybody likes it, you know, we've made the decision that so many people are interested in the 4014, we want to continue, I guess you could say, ride that wave of enthusiasm that people have for that locomotive. Once we get to cover most of the system, I think it's pretty well understood that we'll start balancing out both locomotives a little bit. But for right now, people really, they're just enamored with the 4014. Very, very good question.
So what do you do to treat the water as you're refilling?
Well, I was afraid somebody was going to ask me that. No, well, it's a very good question. And the water treatment is something that is, as I mentioned, it's a very important part of this. So, and you look at any given water here, depending on whether it was processed through reverse osmosis or however they filtered it, there will be stuff in the water. And that stuff in the water could be any stuff. It's just the total dissolved solids of all different types of things. And so you have to manage that. We soften it so that through an ion exchange removes the scaling minerals of calcium and some magnesium and a few other little minor things there. So that takes care of the scaling problem, which was those big photographs that you see. Well, then the other part of it is the TDS, that total dissolved solids will continue to accumulate, and that's what Paul does. And so every day that we're working on this, and Paul works with Bill. Bill has a proprietary chemical called Turlin that his company sells. It's a very good product that helps manage kind of a broad spectrum of things. And then through the softening process, by taking out all of the scaling minerals, now we just have to deal with what's in the water. And that's going to vary everywhere we go. So going forward, we're in the process of buying what's called a nanofiltration system, and it's a big unit. And that unit will go in one of our cars. We're rebuilding one of our cars. And so we'll have the ability to filter it just as a municipal water treatment facility would handle their water. The challenge is that you don't, the water, when you get it too good, is not good for a locomotive boiler. You know, so you've got to manage the alkalinity, has to be managed, and that's a function of the hardness. And so it's a chess game. And there's not really any practical way for us to know much in advance what the hardness is, what the TDS is, because that kind of flows through the seasons. So what we're doing is we're developing this really all-encompassing process to be able to see what the water is by testing it right then and there, and then determine what our TDS needs to be, what it is in the boiler, what it is in the tender, and then through a combination of filtration and softening, we have the resulting equation in the water that we're delivering to the boiler. Sir?
When you rebuilt the boiler and put in new tubes, did you use original design type steel, or did you go to like more modern stainless alloy? And also, did you do anything, or consider doing anything like in the nickel plating inside the boiler? I think it's practical. You know what I mean?
His question was, when we put the tubes and flues back in the locomotive, I'll summarize, did we use the same comparable materials? Yes. Oftentimes when you think about locomotives and you think about, okay, corrosion, carbon steel, rust, water, oxygen, you're part of the thought process is, well, why don't we just involve other types of alloys that are more resistant to corrosion? The issue with that is that they don't really suit well in the role that we need them to serve as a combustion tube. So we're left with carbon steel. It has some qualities about that in water and that interaction. You just have to manage everything. So the material that we use would be the same material they used back in the old days. So material SA-192 is the specific type of material. And there's not many places, as a matter of fact, we really can't get it in the United States. It's made in Germany. So we import that. Most of the big operators around running big steam locomotives get it all from Bentler. So it's all the same stuff. And in terms of plating the inside of the boiler, there's no electroplating, but we use a paint known as epoxy. And epoxy is probably well over 100 years old. And it is specifically designed to treat the inside of pressure vessels. And that's one of the things when we're inside. Jimmy's with me a lot. Ted, you've been in there a few times. You have to be really careful because the epoxy, it's a really tough coating, but you can't scratch it. And part of the chemical that Bill's providing with us that we're using, well, that stuff is designed to go after anything that's attaching itself to the metal. Well, it doesn't know epoxy is good, and it starts going after the epoxy if we're not careful. So anyway, there's so many little things to manage and so many things to be careful. Being OCD about it will at least help you.
When you're making a long run and you're getting into a congested traffic area, are you considered a priority or a special train, or how do they manage getting you through?
His question was, when we're running along, are we a priority and how do we get through a traffic jam? Well, we planned this trip. They already have our plan. I just sent them to it last week. I sent it to our Harriman Dispatch Center, and they will enter it into a database, which will become what we call a special trains wire. And we have many conference calls between now and the time when we depart. And I'll just tell you that we are departing this year. That's all I'll share with you. And so it's really humbling when you understand what the Union Pacific Railroad is doing to run this train that we are responsible for. So bottom line is, I don't ever want to be a nuisance to them. I've developed a network of friends and influential people that I rarely call because they are running an entire network. They don't need me bugging them about some detail. They know my schedule, they know the deal. If it's some little technical nuance that I might be able to call and remind them, that's one thing. But if there's chaos around me, I'm not bothering anybody, because they already know there's a problem and they know we're here. But generally speaking, they really do everything they can, because they know that we've established that expectation with the communities by announcing our schedule. Okay, we're going to release the schedule here fairly soon. As I mentioned, stay tuned for that. When you see that, you'll be able to almost set your watch to that if we have our way. And that's us running it, but it's them helping us run it. So it's really a great network and a great collaboration with Harriman, knowing that there's a lot of high horsepower people up there that are running the trains, and you're part of the fish swimming, in some cases upstream, it's really special for me. Good question. Sammy?
Yeah, what about using stainless steel for studs or nuts for, say, holding down a dome lid or appliances or cylinder head?
His question was stainless for studs and nuts. And again, it comes down to some of that is AMSME, some of that is a fixture or fastener or a material specification that's called for by code. And carbon steel is called for in that because of stainless can be brittle, stainless can work hardened. We use stainless for cosmetic things or ornamental things. Not so much on the big boy. We haven't done a lot of stainless. We did some stainless on the 844. We put some stainless nuts on the outside. We got some stainless dog dishes, you know where it looks good. But as far as that, it's carbon steel. You just have to service it, prepare it, and take care of it, and it'll last. If it's in an area where you can't do those, then it will deteriorate over time.
Positive train control integration. Positive train control integration.
Yes.
What are you doing on that?
His question was PTC. We have full PTC on the big boy, and we'll have it again this time. All we've done is adapt it from a locomotive that we call the horse. So the locomotive that we have with us, whatever that locomotive is, we call that the horse. It has a very comprehensive computer system that manages the PTC interaction with the network, a set of GPS antennas, and lots of computerized stuff that interfaces with all the locomotive systems. So on a steam locomotive, when we rebuilt the big boy, just as when we rebuilt the 844, we fixed up what we call our safety control system, and that's the system that interfaces with the air brakes that allows something like PTC to put the brakes on the train. So that's essentially what we've done. So we've got a software adjustment that allows the PTC in the 4015, it knows where the front of the 4015 is because the computer says it's 17 feet is the front here. Well, we've got 2 water cars and 135 feet of big boy. Well, so we adjust that so the system knows the front of the train is actually now 300 and some feet up there. And everything else works just as if the 4015 were running the train. And we have an air brake modification where we've adjusted the air brakes so it thinks it's running the train, but it's really not. The 4014 steam engine is running the train. And then through another software modification, we alter or we adjust the number. So the 4415 now is the 4014. So when the dispatcher has any kind of PTC interactions with us, it's all very seamless. And we worked 3,000 some odd miles, but not so much as a burp. Beautiful system. Well, one more gentleman back there.
Does the injector run all the time to put water into the boiler?
That's a good question. The injector run all the time? No. The injectors, we've got 2 of them, a live steam injector on the engineer side, the Nathan 4000, just like in the 844 and the 3900s, and a lot of big locomotives had that style of injector. And we have what's called the exhaust steam injector on the fireman side. So the job of the fireman, Ted, would you like to explain that? Actually, Ted is outstanding at explaining it. So what you're doing is we call the rate at which the locomotive is producing power, that's called the evaporative rate. So the rate at which we are evaporating water, that water is replaced. So anytime the locomotive is underway, we are delivering water back to the boiler. When we're operating the big boys were designed to produce a tremendous amount of power. Well, when we're pulling around this 1,000-ton freight train or passenger train, we really don't produce the power that that locomotive was designed for. So anyway, bottom line, we're intermittently adding that water. If we were to put a big load on that, on the big boy, like let's say we're going to go up Sherman Hill with 3,000 tons, you would be able to adjust that injector to be on continuously to deliver the water that the locomotive is using. On the 844, we're able to do that because it has what's known as a feed water pump. And that pump is just like turning your shower on or off.
Right.
A little bit more water this way, a little bit less water that way, and it literally is a feel by the seat of your pants. I think that's why most people, I see some steam engine guys in here, I think that's why most people really are into the steam locomotive, because you can feel it, and it becomes part of you, and you just know. You don't need some digital thing up there telling you, you're not looking at, you look at your gauges, of course, but you're more part of that. Watching Ted fire, Austin, Jimmy's going to become a fireman, John's going to become a fireman. You know, when they develop that skill,
Yep.
and it's a skill they just know. Very good question.
You used to have tours for the public of your UP steam shop up in Cheyenne every May. Are you ever going to resume that at some point?
His question was, are we going to resume tours in the shop? And I hope so, but COVID has really kind of changed a lot of that, and we're still governed by CDC/FRA rules. So until those kind of really relax to the point to where there's a comfort level, I'm sure we'll resume those, but at this time, no. And the other part of that is that we're a small crew, so we just want to be able to manage all that. Yeah, we will not be participating in depot days, sadly. Yeah. And again, it's driven by CDC.
What are you going to do with the Challenger?
Yes. His question was, why don't we have to run ditch lights? And we are, it's recognized that it's historic equipment. You know, that doesn't say that sometime in the future that there may be a mandate, but at this time there's not. So, but we want to make the locomotive what we call conspicuous. So, you know, we may, I brought a Mars light here. I don't know if anybody's into the Mars light, but we jokingly, this is actually for the Forney Museum. The Union Pacific donated a locomotive to them a few years ago, and it was missing that particular device. And we kind of have fun on social media. A lot of people talk about the Mars light on our other locomotive, the 844. So we're going to put a Mars light on the big boy. How come nobody's laughing? Maybe sometime. Sir, you had a follow-up question for me?
Yeah, what do you guys, what's the plans for the Challenger?
His question was, what's the plan for the Challenger? And at this stage, we don't have any announcements to make on that.
Well, I hope they don't scrap it.
I don't think that would ever happen. There'd be a lot of us that would be laying in front of the bulldozer. Including many of our executives. Yes, sir.
Hi. On your initial run with 4014 out to Utah, you really didn't have much time at all to do shakedown and, you know, find anything that you weren't expecting. How did the engine perform in relation to your expectations on its way out to Utah? And what were the things you learned from that were, say, the first things you went to go work on when you got back to the shop?
That was a good question. His question was, we didn't have much time, and that's right, to do what we call our shakedown runs. It's kind of a funny way to put it. When I talk about to them, my bosses, they kind of chuckle. Shakedown kind of has a financial connotation to it. They don't understand the mechanical aspect of it, so that's become a funny way for me to interact, a shakedown run. But in terms of how it performed outstanding. And there were some things that we just had problems with because we ran out of time. But when we were putting the locomotive together, that thing's huge. We're putting the locomotive together, we knew that by putting together exactly the way that the drawing said, the dimensions and everything, materials and everything, that we knew that the only thing that we need to be concerned with is physically running the locomotive conservatively to give those components time to run in. Remember the movie Titanic, when the captain feels the pressure to get to New York fast, and Mr. Ismay says, was kind of pushing him a little bit. He goes, I prefer not to run the engines until they're run in, properly run in. Well, that was what I was concerned with. And we had planned a very liberal break-in period that was just consumed by the events of life. You know, we got delayed here and there. We had this problem, that problem. Next thing you know, we have the engine ready to go 32 hours before we have to go to Ogden. And we have just more and more problems and more problems. Well, I don't care what happens. We're leaving tonight. Next thing you know, it's sunset, and we're going. And we're going to try to make it to Greeley, and we didn't make it to Greeley. And we were having a problem with the crosshead and all kinds of little things that you just have to be able to be flexible, adjust, adapt, like the Marine Corps motto, adapt, improvise, overcome. And you have to be able to understand that, and the crew, to their credit, Ted, Austin, Jimmy, Garland, Paul, everybody is so adaptable. And I am so thankful for that, because there are times when we've got this well thought out plan and it all goes to, you know what, in a handbasket. Did I answer all your questions?
Was there anything that you wanted to work on as soon as you got back in the shop?
Oh yeah, tons of stuff. Yeah. And things that we knew that we were going to do, and things that I made the judgment that and this is hard for me. I'm a perfectionist. But I'm a perfectionist because I've been around the equipment, and it must be so good that your mind becomes a perfectionist. And it's hard to make the judgment call to let something go that isn't quite right. But you have to be able to compartmentalize all that and still deliver the product. So what we did in 2020, COVID came along. Now we're going to take this apart, and this, and this, and this. And we've got the locomotive so tricked out. And there's still stuff I want to do. There's still a lot of stuff I want to do. But it is absolutely beautiful. The water cars we're working on, we're putting an MU controller in, you know, upgrades. All designed to make it so it's easier on us. You know, we are one of the few shops, you know, our shops deliver excellent products. And the diesel locomotives that they're rebuilding are designed and rebuilt with a very high degree of excellence. There is an assumption that over time, a percentage of those rebuilds are going to have failures of components here and there. Well, our shop is the only shop that can produce a locomotive that can never fail. When we go out for a month, nothing can break down on it because there's so much in that plan that we can't compromise by having some boo-boo. And knock on wood, you know, we've been very fortunate that the workmanship that everybody has done and the diligence that everybody makes, Jimmy's inspections, Ted's inspections, Paul's water treatment, Bill's water treatment, Austin's work, John's welding, Garland's machine work, all of that is exactly what we want it to be. It's a lot of pressure, just a little bit. And thank you, everyone.